Alright guys, so we're going to look at square root and cube root inverses. Alright, so you're given a function and it'll say something like find the inverse or maybe find f inverse. Alright, remember this is the notation for inverse, so that's what it's communicating if you see that. Okay, so you have to remember the whole thing with inverses, no matter the function. Linear, quadratic, square root, cubed root, okay, is you have to switch x and y. Okay, so whether it's on a t-chart, your x and y points switch, domain and range switch, which we'll use here in a second, okay, and x and y switch of the equation. Alright, so you might find it helpful to change your f of x to y, even though that's not necessary, but if that helps, you may want to do that. Okay, and then technically your first step is to switch x and y. So literally where there's an x, you're putting a y. Where there's a y, you're putting an x. So we'll have x equals the square root of y minus 1. Okay, so that's your first step. Switch x and y. And then your second and final step is to solve for y. Get y by itself. Okay, so here's y. So we have to look to see if there's any outside numbers to get rid of first, which there's not. So then you can automatically square both sides to get rid of the square root. So squaring and the square root are inverses. So that's how they undo one another. So you're left with x squared equals y minus 1. Alright, and then we're going to add 1 to get y by itself. So x squared plus 1 equals y. And then remember, we can take that a step further and just change it to that function notation. So f inverse equals x squared plus 1. Alright, so that's its equation. Now, keep in mind what these two functions look like. Alright, so we can do, I have it zoomed in here. Let's do a rough sketch of what this looks like. So this quadratic, okay, x squared, so quadratic, and then it's been translated up 1. So I know my parabola, again, this is just a rough sketch of the graph, okay, has been translated up 1, and it's opening upwards because that a value is positive. So I know it looks like this, right? Okay, let's go to my original. Okay, so the original, kind of off to the side here, is a square root function. Okay, and I know that if that minus 1 is in with the x, x's are crazy, so this is going to translate to the right 1 unit. Alright, so right 1, remember the square root parent function looks like this. It has an endpoint, okay, that was at 2. It has an endpoint at 1, sorry, and then it's going to extend this way unless it's been reflected. Alright, so notice I have what looks like about half of a parabola on a square root function. Okay, and then I have the full parabola here. So our issue is if my original is only half of the parabola per se, because it's a square root function, then my inverse can only be half of this parabola. It can't be both. Okay, the reason why graphically is that inverses reflect over the line y equals x. So my inverse, okay, is going to be on this side. So picture I'm like the worst artist ever, but it would be better for me to make a t-chart and flip my points to make a better graph, okay, but it's going to be like over here. So it can't be the full U-shaped graph. That would be what my inverse looks like. So I only need half of it. So how we do that is by called restricting the domain. Okay, so how we restrict the domain of the inverse is first by finding the range of the original, okay? Because the range of the original, and I'll write this down. Where am I going to put this? Down here. So the range of the original is the domain, or let's make it more specific, is the restricted domain of the quadratic inverse. And really that's true for any function, but since we're specifically trying to restrict the quadratic, that's what we'll look at, okay? Or that's how we'll write it. All right, so we need the range of the original because then that will be the restricted domain we'll add here. So with a domain of, because basically what we're doing is we're going to cut this parabola somehow to where it's only half of it. Okay, so we have to do a rough sketch of this graph, which guess what, we already did. We moved it to the right one, so it's this purple one. Okay, so the range of this function, bottom to top, right? So only look at this purple one. So the lowest point on this graph is 0. Highest point on the graph is infinity. And that's the range. So you take that range of the original, and that becomes the restricted domain of the quadratic. So graphically, what that will look like, if this is my domain, so left to right, so how far left does it go? 0. So what that's saying is, I want it to graph from here forever, to the right forever. So it cuts off this side of the parabola whenever we restrict the domain. And notice that's kind of what my rough sketch looks like over here. Okay? Alright, so let's work another one so you can kind of see that. Okay, so let's do a rough sketch of the original first and get the range of it since we know we're going to have to use that. That might be before it gets messy. Let me do it that way on this one. Okay, so on the original, okay, we know that this is going to go, x's are crazy, so left 2 and down 3. Those are my transformation rules that we've been using all year. Okay, so from 0, 0, we go left 2, down 3. And again, it has an endpoint, because that's what the square root function looks like, and it's going to extend to the right forever unless it's been reflected. Okay, so we need the range of this, because that will be the restricted domain. So range is bottom to top. So the lowest point is -3. Highest point is infinity. So lowest point to highest point. So this original range will become the inverse's restricted domain. Okay, so we'll use that here in a little bit. Okay, so as far as the equation goes, f of x is the same thing as y, so I'm just going to rewrite it. Y equals the square root of x plus 2 minus 3. Alright, so the whole point of inverses is to switch x and y, so x equals y plus 2 minus 3. And then solve for y. So I'm going to add 3. So x plus 3 equals square root of y plus 2. Square both sides. Okay, you would need to expand this, okay, if you were going to put it in standard form, but I'm going to leave it in vertex form, so I'm going to leave the x plus 3 squared as is. Square and square root cancel, so we're left with y plus 2. So the final step to get y by itself is subtract 2. So x plus 3 squared minus 2 equals y, which is my f inverse. Alright, so rough sketch of this quadratic, just so you can get a visual. Transformation rules, this is, x's are crazy. Okay, so that's going to go left 3, down 2. The parabola, the a value is positive, so it's facing up. So again, real rough sketch, right? So again, we need to show that it's not going to be this full parabola that is my inverse. It's only half of this parabola. So that's why we have to take this original range, and that becomes the restricted domain of the inverse. Okay, so this is my function with a domain of -3 to infinity. Notice my domain from -3 to infinity is this half of the parabola, and this half is the restricted part. So that part goes away, and I'm only referencing from -3 to the right. So only that half. Okay? Okay, let's look at one more. And then one OYO. Okay, so let's look at this one. So transformation rules, the +3, we know that goes left. +5, we know that goes up. Okay, but what we haven't looked at so far, like in this video, is what this negative does. And you should know it's a reflection over the x-axis. So let's go ahead and do a rough sketch and get our range, which will become the domain of the inverse. So left 3, up 5, 1, 2, 3, 4, 5, okay, yeah. But then, once you plot that vertex, or the endpoint, I guess I should say, not vertex, the endpoint of the square root, okay, typically it would go up and to the right, but picture up and to the right reflected over the x-axis, so it's flipped. So now it's going to go down to the right. Alright, so this range, bottom to top, okay, this arrow keeps going down and down forever, so the range is -infinity as the lowest point. Highest point is at 5. Alright, so that original range again becomes the restricted domain once we find the inverse. Okay, so now let's find the inverse. We'll have y equals negative square roots of x plus 3 plus 5. So whole purpose of inverses is to switch x and y. So x equals y plus 3 plus 5. Okay, subtract your 5 over. So x minus 5 equals negative square roots of y plus 3. Okay, it's like a -1, right, in front, so let's divide by -1. When I divide by -1, you have to divide both of your terms by -1. So negative x and then plus 5 equals square root of y plus 3. Square both sides. Come over here because I'm running out of room before the OYO. So then we have negative x plus 5 squared equals squared and square root cancel, so y plus 3. Last step is to subtract 3. So we have negative x plus 5 squared minus 3 equals y, which again you can replace with the f inverse. Oh, you can't see that. That might be helpful. And then you would just say with a restricted domain, of that negative infinity to 5. Okay? Alright, so let's look at this OYO. Try that. Pause your screen and see what you can do. Alright, so here's your answer down here. So f inverse is negative x plus 3 squared plus 1 with a domain of negative infinity to 3. Alright, so I'll walk you through the process though, but if you got this, you can go and fast forward through the video. There's one more I want you to see. Okay, but the quick explanation, and again, if you have more specific questions, pause it and ask me. Okay, but the negative is a reflection. It goes right 1, up 3. So here's my rough sketch. So the range of this would be from negative infinity, that's the lowest point. Highest point is positive 3. Okay, so that's how I got the domain down here of negative infinity to 3, because it's the original's range. As far as the equation goes, we flip x and y, subtract your 3 over, so x minus 3 equals negative square roots of y minus 1, divide by the negative 1 in front, okay. When you do so, you have to divide both your terms, so here, so negative x plus 3, that's how I got that. Get rid of the square root by squaring both sides. And then last step is add the 1 over. Okay? So last one, again, pause the video and ask me any questions if you have one more. Okay, so last one, notice we have a cubed root 1. So what's nice about the cubed root ones, I'll do a rough sketch over here, is that cubed root, okay, even if it's been moved to the left 1 and down 5, left 1 and down 5, 1, 2, 3, 4, 5. Remember, the cubed root are those like S ones, and that's the vertical stretch of 2, so it has been vertically stretched by 2. So it looks like this. Well, notice what's the range of a cubed root function? Well, it's going to go down forever and ever and ever, and up forever and ever and ever, right? This is a really bad sketch, but hopefully you get the point. Okay, so the range is negative infinity to positive infinity. So what's nice is any cubed root one won't have a restricted domain because it's infinite, just like its inverse, which is a cubic function, which is this one. No, I put an extra little loop in that one. Like something like that. Okay, and so that would be the cubic function, that's its inverse, and that's infinite as well. So what's nice about the cubed root ones, you don't have to worry about a restricted domain. You can just find the equation. So we'll do x equals 2 times the cubed root of y plus 1 minus 5, but you treat it the same way. Okay, so we'll add 5 to both sides. So x plus 5 equals 2 times the cubed root of y plus 1. 2 times, so to get rid of it, we divide. So x plus 5 over 2 equals the cubed root of y plus 1. To get rid of a cubed root, you cube, or you raise it to the third power like a cubic function. So cube and cube root cancel. So we're left with x plus 5 over 2 cubed equals y plus 1. And then your last step would be to subtract 1. So, I'm running out of room here, but that's okay. So we have minus 1, you just put it on the outside. So we have f inverse is equal to x plus 5 over 2 to the third power minus 1. And no restricted domain, because the original and the inverse are both infinite. Okay? So there's an example of that cubed root one.